Database services. Most applications and services depend on at least one database. A database allows an application to store, organize, and quickly retrieve data. Although you could use flat files to store data, they become increasingly slow to search as the amount of data grows. By relying on a database to perform these tasks, application developers can focus on the application without having to directly interact with a file system to store and retrieve data. Consequently, the availability and performance of a database-backed application depend on the database you choose and how you configure it. Databases come in two flavors: relational and non-relational. Each of these differs in the way it stores, organizes, and lets you retrieve data, so the type of database you choose depends on the needs of the application. In this chapter, you'll learn the differences between these two database types and how to select the right one for your application. You'll also learn how to use the managed database services that AWS provides to get the level of performance and reliability your applications require, as well as how to protect your data and recover it in the event of a database failure. This chapter will introduce 3 different managed database services provided by AWS. Amazon Relational Database Service, or RDS, Amazon Redshift, and finally DynamoDB. Relational databases. A relational database contains at least one table, which you can visualize as a spreadsheet with columns and rows. In a relational database table, columns may also be called attributes, and those rows may also be called records or tuples. So column and attributes. Before you can add data to a relational database table, you must predefine each column's name and what data types it can accept. Columns are ordered, and you can't change the order after you create the table. The ordering creates a relationship between attributes in the table, which is where the term relational database comes from. Refer to Table 5.1 for an example of a relational database table containing employee records. Data must match the type defined under each column. For example, the employee ID can't be a letter because it's defined as a numeric data type. One advantage of a relational database is that it allows for flexible queries. You don't have to understand up front how you're going to query the data. As long as the data in there is there in a consistent format, okay, you can craft queries to get the data you want, the way you want. And this makes relational databases good for applications that need to query data in arbitrary columns and customize how that data is presented. For example, you could query the database to return the birth date of every employee whose first name is Charlotte. Or you could query the database for every employee with a birthday in July. Relational databases make getting the data you want fast and easy. Another advantage is that you can add more columns to the table after creating it. You can also delete columns, but deleting a column entails deleting all the data stored under the column. If you delete the first name column, it will remove first name data for all employees in the table. Using multiple tables. Storing all data in a single table can lead to unnecessary duplication, needlessly increasing the size of the database and making queries slower. Hence, it's common for applications to use multiple related tables. Using the preceding example, if 50 employees work in the information technology department, the string information technology appears in the table 50 times, one for each record. To avoid this wasted space, you may create a separate table to hold department names, as shown in Table 5.2. Instead of putting the department names in every employee record, you'd create a single record for each department in the departments table. The employees would then refer to each department using the department ID, as shown in table 5.3. In this relationship, the departments table is the parent table, and the employees table is the child table. Each value in the department column in the employees table refers to the department ID in the departments table. Notice that the data type for the departments column is still a string. Although you could change the data type to a number, it's not necessary. The department ID in the departments table is called the primary key, and it must be unique in the table so that it can uniquely identify a row. The employees table refers to the department ID as a foreign key. You must define primary and foreign keys so that the database knows how the columns in different tables are related. The database will enforce foreign key constraints to ensure that when a child table references a foreign key, that key also exists in the parent. Note: there's a common misconception that the relational in relational database refers to the relationship between tables, but the relational aspect refers to the relationship of attributes within a row. In other words, all the attributes in a row are related to each other in some way. To better understand this, imagine a relational database with only one table. Even though there are no relationships between tables, it's still a relational database. Structured query language. You use the structured query language, or SQL, with relational databases to store and query data and perform database maintenance tasks. For this reason, relational databases are often called SQL databases. SQL commands, or statements, differ slightly depending on the specific relational database management system you're using, or the specific RDBMS you're using. All major programming languages have libraries that construct SQL statements and interact with the database, so you don't need to master SQL, but you do need to understand the concepts behind a few common SQL terms. Querying data. The select statement is used to query data from an SQL database. It allows you to query based on the value in any column, as well as specify the specific columns you want the database to return. Thanks to the predictable structure of tables and the enforcement of foreign key constraints, you can use a join clause with a select statement to join together data from different tables. Storing data. The insert statement allows you to insert data directly into a table. For example, when adding new customer information to a customer relationship management application, the application is probably using an SQL insert on the back end to add the customer data to the table. If you need to load a large number of records into a database, you can use the copy command to copy data from a properly formatted file into the table you specify. Online transaction processing versus online analytic processing. A relational database can be optimized for fast, frequent transactions, or it can be optimized for large, complex queries. Depending on its configuration, a relational database can fall into one of two categories: online transaction processing, or OLTP, or online analytic processing, or OLAP. OLTP. OLTP, online transaction processing databases, they're suited to applications that read and write data frequently, on the order of multiple times per second. They're optimized for fast queries, and those queries tend to be regular and predictable. Depending on the size of the database and its performance requirements, an OLTP database may have intense memory requirements so that it can store frequently accessed portions of the table in memory for quick access. Generally, a single server with ample memory and compute power handles all the writes to an OLTP database. An OLTP database would be a good candidate for backing an online ordering system that processes hundreds of orders a minute. OLAP, online analytic processing databases, are optimized for complex queries against large datasets. As a result, OLAP databases tend to have heavy compute and storage requirements. In data warehousing applications, it's common to aggregate multiple OLTP databases into a single OLAP database. For example, in an OLTP database for an employee management system, employee data may be spread out across multiple tables. At regular but infrequent intervals, a data warehouse would aggregate those tables into a single table in an OLAP database. And that makes it easier to structure SQL queries against the data. It also reduces the amount of time it takes to process a computationally intensive query by offloading it to the high-powered OLAP database, the online analytic processing database. With a large OLAP database, it's common for multiple database servers to share the computational load of the complex queries. In a process called partitioning or sharding, each server gets a portion of the database for which it's responsible. Amazon Relational Database Service. Amazon Relational Database Service, or RDS, is a managed database service that lets you run relational database systems in the cloud. RDS takes care of setting up the database system, performing backups, ensuring high availability, and patching the software and the underlying OS. RDS also makes it easy to recover from database failures, restore data, and scale your databases to achieve the level of performance and availability that your application requires. To deploy a database using RDS, you start by configuring a database instance, which is an isolated database environment. A database instance exists in a virtual private cloud that you specify. But unlike an EC2 instance, AWS fully manages database instances. You can't establish an SSH session to them, and they don't show up under your EC2 instances. Database engines. A database engine is simply the software that stores, organizes, and retrieves data in a database. Each database instance runs only one database engine. RDS offers the following 6 database engines to choose from. So we've got MySQL, MariaDB, Oracle, Postgres, Amazon Aurora, and Microsoft SQL Server. So MySQL, that's designed for online transaction processing applications, such as blogs and e-commerce. RDS offers the latest MySQL Community Edition versions. MySQL offers 2 storage engines, MyESAM and InnoDB. But you should use the latter, InnoDB, as it's the only one compatible with RDS managed automatic backups. MariaDB is a drop-in binary replacement for MySQL. It was created over concerns about MySQL's future after Oracle acquired the company that developed it. MariaDB supports the ExtraDB and InnoDB storage engines, but AWS recommends using the latter, InnoDB, for maximum compatibility with RDS. The third engine, Oracle. Oracle is the most widely deployed relational database management system. Some applications expressly require an Oracle database. RDS provides the following Oracle database editions: Standard Edition 1, or SC1, Standard Edition 2, or SC2, Standard Edition SE, and Enterprise Edition EE. Postgres. Postgres advertises itself as the most Oracle-compatible open source database. This is a good choice when you have in-house applications that were developed for Oracle but want to keep costs down. Amazon Aurora. Aurora is Amazon's drop-in binary replacement for MySQL and Postgres. Aurora offers better write performance than both by using a virtualized storage layer that reduces the number of writes to the underlying storage. It provides two editions, MySQL compatible, Postgres compatible. Depending on the edition you choose, Aurora is compatible with Postgres or MySQL import and export tools and snapshots. Aurora is designed to let you seamlessly migrate from an existing deployment that uses either of those two open source databases. For MySQL compatible editions, Aurora supports only the InnoDB storage engine. Also, the Aurora Backtrack feature for MySQL lets you, within a matter of seconds, restore your database to any point in time within the last 72 hours. Finally, number 6, Microsoft SQL Server. RDF offers multiple Microsoft SQL Server versions, ranging from 2012 to the present. For the edition, you can choose Express, Web, Standard, or Enterprise. The variety of flavors makes it possible to migrate an existing SQL Server database from an on-premises deployment to RDS without having to perform any database upgrades. Licensing considerations. RDS provides two models for licensing the database engine software you run. The license included model covers the cost of the license in the pricing for an RDS instance. The bring your own license, or BYOL, model requires you to obtain a license for the database engine you run. License included. MariaDB and MySQL use the GNU General Public License GPL version 2.0, and Postgres uses the Postgres license, all of which allow for free use of the respective software. All versions and editions of Microsoft SQL Server that you run on RDS include a license, as do Oracle Database Standard Edition 1 and Standard Edition 2. And then bring your own license, well, only the Oracle database engine supports this model. The following database editions allow you to bring your own license: EE Enterprise Edition, Standard Edition, Standard Edition 1 and Standard Edition 2. So all the four we mentioned allow bring your own license. Database option groups. Different database engines offer various features or options to help you manage your database and improve security. Option groups let you specify these features and apply them to one or more instances. Options require more memory, so make sure your instances have ample memory and enable only the options you need. The options available for a database option group depend on the engine. Oracle offers Amazon S3 integration. Both Microsoft SQL Server and Oracle offer transparent data encryption, or TDE, which causes the engine to encrypt data before writing it to storage. MySQL and MariaDB offer an audit plugin that lets you log user logons and queries run against your database. Database instance classes. When launching a database instance, you must decide how much processing power, memory, network bandwidth, and disk throughput it needs. RDS offers a variety of database instance classes to meet the diverse performance needs of different databases. If you get it wrong or your needs change, you can switch your instance to a different class. RDS divides database instance classes into the following three types. So we have standard, memory optimized, and finally burstable performance. Standard instance classes meet the needs of most databases. The latest generation instance class is db.m5, which provides up to 384 gig of memory, 96 virtual CPUs, 25 gigabits per second of network bandwidth, and 19,000 megabits per second of disk throughput. Memory optimized. Memory optimized instance classes are for databases that have hefty performance requirements. Providing more memory to a database allows it to store more data in memory, which can result in faster query times. There are 3 latest generation instance classes: db.x1e, db.z1d, and db.r5, and the most powerful of these is db.x1e, and that provides up to 3,904 gig of memory, 128 virtual CPUs, like before, 25 gigabits per second of network bandwidth, and then we've got slightly lower disk throughput here. It was before 19,000, it's now 14,000 megabits per second of disk throughput. Database instances use EBS storage. Both the standard and memory optimized instance class types are EBS optimized, meaning they provide dedicated bandwidth for transfers to and from the EBS storage. And finally, the third type, burstable performance. These are for development, test, and other non-production databases. The latest burstable performance instance class available is db.t3, and that gives you up to 32 gig of memory. So standard had 384 gig of memory as a comparison, and then for memory optimized we of course went to over 3,000 gig. So here we've got 32 gig of memory, just 8 virtual CPUs as opposed to 96 or 128, 5 gigabits per second of network bandwidth, and just over 2,048 megabits per second of disk throughput. The db.t3, db.m5, which was in the standard class, and db.r5, which was memory optimized, those classes are based on the AWS Nitro system, accounting for significantly improved performance over older generation instance classes. Note that disk reads and writes count against the maximum disk throughput on these instance classes. Storage. Selecting the right storage for your database instance is more than just ensuring you have enough disk space. You also have to decide how fast the storage must be to meet the performance requirements of your database-backed application. Understanding input-output operations per second. AWS measures storage performance in input-output operations per second. An input-output operation is either a read from or a write to storage. All things being equal, the more IOPS you can achieve, that's IOPS, input-output operations per second, IOPS. So the more IOPS you can achieve, the faster your database can store and retrieve data. RDS allocates you a number of IOPS, depending on the type of storage you select, and you can't exceed this threshold. The speed of your database storage is limited by the number of IOPS allocated to it. The amount of data you can transfer in a single I/O operation depends on the page size that the engine uses, the database engine. To understand how many IOPS you need, you first need to understand how much disk throughput you need. Before we look at a few examples, a little warning. The math can get tricky, but you don't need to memorize all the details. Just make sure you understand what IOPS actually measure. MySQL and MariaDB have a page size of 16 kilobytes. Hence, writing 16 kilobytes of data to disk would constitute one I/O operation. Oracle, Postgres, and Microsoft SQL Server, they use a page size of 8 kilobytes as opposed to 16. Writing 16 kilobytes of data using one of these database engines would consume 2 I/O operations because they have that smaller page size. The larger the page size, the more data you can transfer in a single operation. Assuming a 16 kilobyte page size, like with MySQL and MariaDB, suppose your database needed to read 102,400 kilobytes of data every second. To achieve this level of performance, your database would have to be able to read 6,400 16 kilobyte pages every second. Because each page read counts as one I/O operation, your storage and instance class would need to be able to sustain 6,400 IOPS, so 6,400 operations every second. Note the inverse relationship between IOPS and page size. The larger your page size, the fewer IOPS you need to achieve the same level of throughput. Note, things get interesting when you move beyond a 32 kilobyte page size. If your database engine writes more than 32 kilobytes in a single I/O operation, AWS counts that as more than one I/O operation. For example, reading or writing a 64 kilobyte page would count as 2 operations. A 128 kilobyte page would count as 4 I/O operations. End of note. The number of IOPS you can achieve depends on the type of storage you select. RDS offers the following 3 types of storage. So we've got general purpose SSD, provisioned IOPS SSD, and then we will discuss HDD, which is hard disk drive. So 2 kinds of solid state drive, or SSD, and then we move on to throughput optimized. So first of all, general purpose SSD. For most databases, general purpose SSD, which is denoted by GP2, is sufficient. It's fast, giving you single-digit millisecond latency. You can allocate a volume of up to 64 terabytes. For each gigabyte of data that you allocate to a volume, RDS allocates that volume a baseline performance of 3 IOPS, up to a total of 16,000 IOPS per volume. A 20 gig volume would get 60 IOPS, whereas a bigger volume, a 100 gig volume, would get 300 IOPS. A 5,334 gigabyte volume would get 16,000 IOPS. This means that the larger your volume, the better performance you'll get. Note that the minimum storage volume you can create is 20 gig. The maximum throughput the GP2 storage type offers is 2,000 megabits per second. To achieve this, 2 things have to fall into place. First, your instance must support a disk throughput of at least that much. For example, all db.m5 instance classes supported a throughput of 4,750 megabits per second, so any one of those would suffice. Also, you must allocate a sufficient number of IOPS to sustain that throughput. Suppose you're running MariaDB with a page size of 16 kilobytes, as we know that, and MySQL has that page size. To determine the number of IOPS you'll need to sustain 2,000 megabits per second of throughput, you'd divide the bandwidth by the page size as follows. So we would do 2,000 megabits per second. So the assumption is we want to achieve the maximum throughput for GP2, which is 2,000 megabits per second. So we're going to do 2,000 megabits per second, and we're going to divide that by the page size, which is, as we said, 16 kilobytes, but that turns out to be just 0.128 megabits. So we do 2,000 divided by 0.128, and of course that's going to produce a very large number, and that will give us the IOPS. It turns out to be just over 15,000 IOPS. So we do 2000 megabits per second divided by 0.128, and that gives us 15,625 IOPS. So as we said two things have to fall into place to get that maximum throughput. We've got to have the right instance class, and we've also got to have the IOPS in place to back up that throughput. And we were just doing a quick calculation to work out how much IOPS we really do have to allocate to achieve that throughput. So to achieve 2000 megabits per second disk throughput on a volume, it would need 16,000 IOPS allocated. Note that you must specify provisioned IOPS in increments of 1,000. Also, as stated earlier, this is the maximum number of IOPS possible with GP2, 16,000. To achieve this many IOPS, your volume would have to be 5,334 gigabytes, or about 5.33 terabytes big. The IOPS is linked to the size of the volume. If you think you might occasionally need up to 3,000 IOPS, but don't need a lot of storage, you don't have to over-allocate storage just to get your desired number of IOPS. Volumes smaller than 1 terabyte can temporarily burst to 3,000 IOPS. The duration of the burst is determined by the following formula. So the burst duration in seconds is going to be equal to the following fraction. So on the top you're going to have the credit balance, and you're going to divide whatever your credit balance is by 3,000, take away 3 lots of the storage size in gigabytes. When you initially boot a database instance, you get a credit balance of just over 5,400,000 IOPS. Whenever your instance uses IOPS above and beyond its baseline, it will dip into the credit balance. And after that credit balance is depleted, you can no longer burst. For example, with a 200 gigabyte volume, the burst duration in seconds would be 2,250 seconds. And of course you can work that out with our equation, because all you need to put into the equation to get that duration in seconds is your credit balance on the top, and then on the bottom, the denominator, you have 3,000 to take away 3 multiplied by your storage size. So if we plug the credit balance in and the storage size, we can always work out the burst duration. And as we've said here, if you happen to have a 200 gigabyte volume, that duration would be just over 2,000 seconds, which is about 38 minutes. That credit balance is replenished at a rate of 1 baseline IOPS every second. For example, if you have a 200 gigabyte volume with a baseline IOPS of 600, your credit balance increases by 600 IOPS per second, up to the maximum of 5,400,000. To get some practice with these concepts, complete exercise 5.1 to create an instance using that GP2 storage. We now move from GP2, or general purpose SSD, to provisioned IOPS SSD. Now, provisioned IOPS SSD is sometimes denoted with IO1, so the letter number IO1. If you're not excited about the rather confusing math involved with using GP2 storage, RDS provides a more straightforward option, provisioned IOPS SSD, which lets you simply allocate the number of IOPS you need when you create your instance. There's no concept of bursting in IO1 storage. The number of IOPS you provision is what you get and what you pay for, whether or not you use it. This makes it useful for databases that require consistent, low latency performance. If you use a standard or memory optimized instance class, RDS guarantees that you'll achieve within 10% of the provisioned IOPS for 99.9% of the year. That means you may get less than your specified number of IOPS for only about 2 hours and 45 minutes out of the year. You can provision up to 64,000 IOPS per volume with IO1. Compare that to the 16,000 before. The maximum number of IOPS you can achieve and how much storage you can allocate depend on the database engine you select. Oracle, Postgres, MariaDB, MySQL, and Microsoft Server, and Aurora. Okay, so that's all the 6 we mentioned earlier. All of them let you choose 4 GB up to 16 terabytes of storage and allocate up to 64,000 IOPS. The ratio of storage in gigabytes to IOPS must be at least 50 to 1. So, for example, if you want 32,000 IOPS, you must provision at least 640 gigabytes of storage. Now on to HDD. Throughput optimized HDD volumes use magnetic storage. Volume sizes range from 500 megabytes to 16 terabytes. Again, that cap of 16 terabytes seems to apply to every volume we've looked at. Apart from general purpose SSD, that's actually 64 terabytes. The very first one, GP2, that's 64 terabytes. Here, just 16 terabytes. So that's the volume sizes for throughput optimized HDD. I should say there are 2 kinds of hard disk drive storage you can get. One of them is known as throughput optimized, where we're making throughput the main concern, and that's often denoted as ST1. You can imagine that standing for Super Throughput 1. There's also another variety of HDD which is called cold HDD, denoted often by SC1. You can imagine standing for Super Cold 1. So for throughput optimized ones, 500 megabytes up to 16 terabytes, the base throughput, that depends on the volume size, with 40 megabits per second of throughput for every terabyte in size. And that maximum throughput tops out at 500 megabits per second for a 16 terabyte volume. Cold HDD volumes also use magnetic storage, and they come in sizes ranging from 500 megabytes to 16 terabytes, just like before. The difference is that SC1 volumes offer lower throughput. You only get 12 megabits per second of throughput per terabyte. So compare that to 40 megabits per second per terabyte. 40 down to 12 per terabyte, with a maximum of 192 megabits per second for a 16 terabyte volume. As you might expect, SC1 is cheaper than ST1 storage. Note, the ST1 and SC1 volume types are appropriate for frequent, sequential, as opposed to random reads and writes. Such as you might see with data warehousing, extract, transform and load jobs, and elastic MapReduce applications. These volume types are not appropriate for random I/O. For that, GP2 is a better choice. End of note. And finally, magnetic storage. RDS offers magnetic storage for backward compatibility with older instances. It's limited to a maximum size of a terabyte and approximately 100 IOPS. AWS is phasing out this storage type, so don't use it. Read replicas. Now this discussion is about improving performance. It's not chiefly about failover. If your database instance doesn't meet your performance requirements, you have the option to scale up vertically or scale out horizontally, depending on where the bottleneck is. So first of all, scaling vertically or scaling up. As mentioned previously, if your memory, compute, network speed or disk throughput are the issue, you can simply throw more resources at your instance without having to make any changes to the application or databases. The way you do that is by upgrading to a larger instance class. This is called scaling vertically or scaling up. Scaling horizontally. Scaling horizontally, also known as scaling out, entails creating additional instances called read replicas. All database engines, except for Microsoft SQL Server, support read replicas. Aurora exclusively supports a specific type of read replica called an Aurora replica. A read replica is another database instance that services only queries against the database. A read replica takes some of the query load off the master database instance, which remains solely responsible for writing data to the database. Read replicas are useful for read-heavy applications. You can have up to 5 read replicas for RDS and up to 15 Aurora replicas. Data from the master is asynchronously replicated to each read replica, meaning there's a delay between when the data is written to the database by the master and when it shows up on the replica. Depending on how much data you can stand to lose, this can make read replicas unsuitable for disaster recovery. If the master database instance fails before the replication is complete, you will lose some unsynchronized data. When you create a read replica, RDS gives you a read-only endpoint, which is a domain name that resolves only to your read replica. And if you have multiple replicas, RDS will load balance the connection to each one of them. If you have reporting and analysis tools that only need to read data, you would point them to a read-only endpoint. Complete exercise 5.2 to create a read replica for the database instance you created earlier. A read replica and the master may be in different availability zones and even in different regions. In the event of the master instance failing, you can promote a read replica to the master. Okay, there we go. So actually this discussion isn't just about performance, it is also about when things go wrong, not just improving when things are going well. So you can promote a read replica to the master, but keep in mind that because of the asynchronous nature of that replication, you may lose data this way. Complete exercise 5.3 to promote your read replica to a master. High availability now, multi-AZ. To keep your database continuously available in the event of a database instance outage. For this, you can deploy multiple database instances in different availability zones, using what RDS calls a multi-AZ deployment. In a multi-AZ deployment, you have a primary database instance in one availability zone that handles reads and writes to the database, and you have a standby database instance in a different availability zone. If the primary instance experiences an outage or fails, it will fail over to the standby instance, usually within 2 minutes. Here are a few possible causes for a database instance outage: availability zone outage, changing a database instance type, patching one of the instance's OSs. You can configure multi-AZ when you create a database instance or later. All database engines support multi-AZ, but implement it slightly differently. If you enable multi-AZ after creating your instance, you'll experience a significant performance hit, so be sure to do it during a maintenance window. Multi-AZ with Oracle, Postgres, MariaDB and MySQL, and Microsoft SQL Server. So that's all the engines apart from Aurora. In this multi-AZ deployment, so for those 5 database engines, you've got the 2 big corporate ones, Oracle and Microsoft, and then the 2 open source ones, MySQL and Postgres. Maria is just within MySQL really. So for multi-AZ with these, all instances must reside in the same region. RDS synchronously now. So before we mentioned with the read replicas, we said they have asynchronous replication, and we said if you want to rely on the fact that you can just promote a read replica to the master, you might lose some data. That was asynchronous replication we talked about there. Well, we're now talking about synchronous replication, and we're saying RDS synchronously replicates data from the primary to the standby instance with multi-AZ, and this replication can introduce some latency, so be sure to use EBS optimized instances and provisioned IOPS SSD storage. Don't use HDD. Your application connects to the endpoint domain name for the primary. Note that the standby instance is not a read replica and cannot serve read traffic. It's a standby. When a failover occurs, RDS changes the DNS record of that endpoint to point to the standby. The only thing your application has to do is reconnect to the endpoint. For MySQL and MariaDB, you can create a multi-AZ read replica in a different region. Okay, so for those ones we're combining the idea of read replicas, which chiefly helps with performance, with this idea of multi-AZ, which is chiefly for failing over when faults happen. So with MySQL and its drop-in replacement MariaDB, you can create a multi-AZ read replica in a different region. This lets you fail over to a different region, but multi-region failover isn't supported for Microsoft SQL Server, Postgres, or Oracle. Presumably it is possible then for Aurora. Yeah, we know it is. Note that if you configure multi-AZ using the bring your own license model for Oracle, you must possess a license for both the primary and the standby instances. Okay, here we go. So now multi-AZ with Amazon Aurora. Amazon Aurora gives you 2 options for multi-AZ, single master and multi-master. An Amazon Aurora single master cluster consists of a primary instance. Aurora gives you a cluster endpoint that always points to the primary instance. An Aurora cluster also may include Aurora replicas, so things which are there optimizing performance. They're not just stepping in when things go wrong, they're replicas. The primary and all replicas share a single cluster volume, which is synchronously replicated across 3 availability zones, and this cluster volume automatically expands as needed, up to 64 terabytes. In the event the primary instance fails, one of 2 things will happen. If no Aurora replicas exist, Aurora will create a new primary instance to replace the failed one, and if an Aurora replica does exist, Aurora will promote that replica to the primary, and the entire process typically takes less than 2 minutes. As we mentioned when we just introduced multi-AZ, less than 2 minutes. So that's single master with Aurora. There's also multi-master. In a multi-master cluster, all instances can write to the database. Thus, when one instance fails, no failover even occurs because all instances can continue to write to the shared cluster volume that stores the database. Amazon refers to this as continuous availability rather than high availability, because as long as at least one database instance is running, you can read from and write to the database. So that's multi-master on Aurora, which is one of the 2 ways in which it implements the multi-AZ feature. backup and recovery. With RDS, you can take EBS volume snapshots of your database instances. Snapshots include all databases on the instance, and they're stored in S3, just like regular EBS snapshots. Snapshots are kept in multiple zones in the same region for redundancy. Taking a snapshot suspends all I/O operations for a few seconds unless you're using multi-AZ with a database engine other than Microsoft Server. Be sure to take your snapshots during off-peak times. When considering your backup and recovery needs, you should understand two metrics: the recovery time objective, the maximum acceptable time to recover your data and resume your processing after a failure has occurred, and then the recovery point objective, the maximum period of acceptable data loss. Consider your own RTO and RPO requirements when choosing your RDS backup options. So the RTO looks to the period of time after the catastrophic event, but the recovery point objective is more backward facing. It considers the period of time and how large it is, which contains lost data. So the recovery point objective considers how much time can possibly pass between your last backup and the catastrophic event. If you're backing up every 5 minutes, because that's your objective to do that, your aim, then you're only ever going to lose a maximum of 5 minutes worth of data. I mean, the probability is that you don't even lose that, because it might happen, the catastrophic event might happen just 1 minute after your last backup. So that's RTO and RPO. The recovery time objective is about how long it takes you to get things sorted after the catastrophic event. It doesn't look back to the time period between your last backup and the catastrophic event. So yeah, to help with those two metrics, you can use snapshots of your EBS volumes, and your EBS volumes contain the data of your database. So when you restore from a snapshot, RDS restores it to a new instance. The time to restore a snapshot can take several minutes depending on its size. The more provisioned IOPS you allocate to your instance, the faster that recovery time will be. Automated snapshots. RDS can automatically create snapshots of your instances daily during a 30-minute window. You can customize this window or let RDS choose it for you. Because taking a snapshot does impact performance, choose a time when your database is least busy. If you let RDS select the backup window, it will randomly select a 30-minute window within an 8-hour block that varies by region. Enabling automatic backups enables point-in-time recovery, which archives database change logs to S3 every 5 minutes. In the event of a failure, you'll lose only up to 5 minutes worth of data. Restoring to a point in time can take hours, depending on how much data is in the transaction logs. RDS keeps automated snapshots only for a limited period of time, and then it deletes them. You can choose a retention period between 1 day and 35 days. The default is 7 days. To disable automated snapshots, you're just going to set the retention period to 0. Note that disabling automated snapshots immediately deletes all existing automated snapshots and disables also that point-in-time recovery. Also, if you change the retention period from 0 to any other value, it will trigger an immediate snapshot. You can also manually take a snapshot of your database instance. Unlike automated snapshots, manual snapshots will stick around until you delete them. If you delete an instance, RDS will prompt you to take a final snapshot. It will also prompt you to retain those automated snapshots, and RDS will keep the final snapshot and all manual snapshots. If you choose not to retain automated backups, it will immediately delete any automated snapshots. Finally, on RDS, maintenance items. Because RDS is a managed service, it's the responsibility of AWS to handle patching and upgrades. AWS routinely performs these maintenance items on your database instances. Maintenance items include operating system security and reliability patches. These generally occur once every few months. Database engine upgrades may also occur during a maintenance window. When AWS begins to support a new version of a database engine, you can choose to upgrade to it. Major version upgrades may contain database changes that aren't backward compatible. As such, if you want major version upgrade, you must apply it manually. AWS may automatically apply minor version changes that are non-breaking. You can determine when these maintenance tasks take place by specifying a 30-minute weekly maintenance window, and the window cannot overlap with the backup window. Even though the maintenance window is 30 minutes, it's possible for tasks to run beyond this. Now, Amazon Redshift. Recall from earlier in the chapter that OLAP database, online analytic processing databases, are optimized for data warehousing applications wherein multiple databases are fed into or aggregated into a single monster database, optimized for those complex, computationally intensive queries. Well, Redshift is Amazon's managed data warehouse service. Although it's based on Postgres, it's not part of RDS. Redshift uses columnar storage, meaning that it stores the values for a column close together. And this improves storage speed and efficiency and makes it faster to query data from individual columns. Redshift supports Open Database Connectivity, or ODBC, and Java Database Connectivity, or JDBC, those two database connectors. Redshift uses compression encodings to reduce the amount of size each column takes up in storage. You can apply compression manually or on a column by column basis. Or if you use the copy command to import data from a file into a Redshift database, Redshift will determine which columns to compress. Compute nodes. So a Redshift cluster contains one or more compute nodes that are divided into two categories. Dense compute nodes can store up to 326 terabytes of data on magnetic storage. Dense storage nodes can store up to 8,192 terabytes of data on fast SSDs. So we made the shift there from just over 300 terabytes to over 8,000 terabytes. That's dense compute nodes and dense storage nodes. If your cluster contains more than one compute node, Redshift also includes a leader node to coordinate communication among the compute nodes, as well as to communicate with clients. A leader node doesn't incur any additional charges. Data distribution styles. Rows in a Redshift database are distributed across the compute nodes. Now, how the data is distributed depends on the distribution style. So there's even distribution, key distribution, and all distribution. In even distribution, the leader node spreads the data out evenly across all compute nodes. This is the default style. Key distribution spreads the data according to the value in a single column, and columns with the same value are stored on the same node. In the all distribution, every table is distributed to every compute node. Redshift Spectrum. Redshift Spectrum is a service that allows you to query data from files stored in S3 without having to import the data into your cluster. You simply define the structure of the data and then query it as you wish. The bucket containing the data you want to query must be in the same region as your cluster. AWS Database Migration Service. The AWS Database Migration Service, or DMS, can automatically copy an existing database and its schema, if that's applicable, to another database. What makes DMS particularly powerful is its ability to migrate database between different database engines and between relational and non-relational databases. DMS can migrate data between the following. We've got Aurora, DynamoDB, IBM DB2, MariaDB and MySQL, which we've mentioned earlier, but also MongoDB. We've got S3, we've got Redshift, Postgres, so we've got Postgres along with MySQL and its siblings. We've got SAP, so it can migrate between all of those things. We've got about 11 bullet points. Now, DMS, the Database Migration Service, provisions an EC2 instance called a DMS instance. That's the brains behind DMS. It initiates connections to the source and target databases and performs the replication and any necessary schema conversions between them. Note, if you need to migrate a database that's too large to transfer over the network, you can use Snowball Edge instead. More information on that is in Chapter 3. End of note. Non-relational or NoSQL databases. Non-relational databases are designed to consistently handle tens of thousands of transactions per second. Although they can store the same data you'll find in a relational database, they're optimized for so-called unstructured data. Unstructured data is an unfortunate term, as all the data in any database has some structure. A more accurate description would be multi-structured data. The data you store in a non-relational database can vary in structure, and that structure can change over time. Non-relational and relational databases have many elements in common. Non-relational databases, or NoSQL databases, consist of collections that are confusingly also sometimes called tables. Within a table you store items, which are similar to rows or tuples in a relational database. Each item consists of at least one attribute, which is analogous to a column in an SQL database. An attribute consists of a unique name called a key, a data type, and a value. Attributes are sometimes called key-value pairs. One of the biggest differences between a relational and a non-relational database is that non-relational databases are schema-less and don't require all items in a table to have the same attributes. Each item requires a primary key attribute whose value must be unique within the table. The purpose of the primary key is to uniquely identify an item and provide a value by which to sort items. Non-relational databases are flexible when it comes to the type of data you can store. With the exception of the primary key attribute, you don't have to define attributes when you create a table. You create attributes on the fly when you create or modify an item. These attributes are unordered and hence have no relation to each other, which is why they're called non-relational. Non-relational databases do not give you a way to split data across tables and then merge it together at query time. Therefore, an application will generally keep all its data in one table. This can lead to the duplication of data, which in a large database can incur substantial storage costs. Querying data. The trade-off for having flexibility to store unstructured data comes in terms of being more limited in your queries. Non-relational databases are optimized for queries based on the primary key. Queries against other attributes are slower, making non-relational databases inappropriate for complex or arbitrary queries. Prior to creating a table, you need to understand the exact queries you're going to need to perform against the data. Consider the item represented in table 5.4. Imagine a database with millions of such items. If you wanted to list every department that has an employee named Charlotte, it would be difficult to obtain this information using a non-relational database. Because items are sorted by employee ID, the system would have to scan through every item to locate all items that have an attribute first name, which has a value of Charlotte. And because the data in each item is unstructured, it may require searching through every attribute within each item. It would then have to determine which of these items contains a department attribute. Such a query would be slow and computationally expensive. Types of non-relational databases. You may hear non-relational databases divided into categories such as key-value stores, document-oriented stores, and graph databases, but all non-relational databases are key-value store databases. A document-oriented store is a particular application of a non-relational database that analyzes the contents of a document stored as a value and extracts metadata from it. A graph database, such as Amazon Neptune, analyzes relationships between attributes in different items. This is different than a relational database that enforces relationships between records. A graph database discovers these relationships in that unstructured data. DynamoDB. DynamoDB is a managed non-relational database service that can handle thousands of reads and writes per second. It achieves this level of performance by spreading your data across multiple partitions. A partition is an allocation of storage for a table, and it's backed by solid-state drives in multiple availability zones. Partition and hash keys. When you create a table, you must specify a primary key and a data type. Because that primary key uniquely identifies an item in the table, its value must be unique within the table. There are two types of primary keys you can create. A partition key, also known as a hash key, is a primary key that contains a single value. When you use only a partition key as a primary key, it's called a simple primary key. Good candidates for a partition key would be an email address, a unique username, or even a randomly generated identifier. A partition key can store no more than 2048 bytes. A primary key can also be a combination of two values, a partition key and a sort key, or a range key. And so that's called a composite primary key. The partition key doesn't have to be unique, but the combination of the partition key and the sort key must be unique. For example, a person's last name could be the partition key, whereas the first name could be the sort key. Using this approach, you could use the values in table 5.5 for a composite primary key for a table. Neither the last name Lewis nor the first name Warren is unique within the table. But combining the partition and sort keys together creates a unique primary key. DynamoDB distributes your items across partitions based on the primary key. Using the preceding example, items with the last name Lewis would all be stored together on the same partition. DynamoDB would arrange the items in ascending order by the sort key. Note that a sort key can store no more than 1024 bytes. When a lot of read or write activity occurs against items stored in the same partition, the partition is said to be a hot partition. Hot partitions can negatively affect performance. To avoid hot partitions, try to make your partition keys as specific as possible. For example, if you're storing log entries, consider using a timestamp that changes frequently as the partition key. And that will mean that there's actually not too much on one particular partition key, or we have a more even spread in terms of how the read or writes occur on all our partitions. Attributes and items. Each key value pair composes an attribute, and one or more attributes make up an item. DynamoDB can store an item size of up to 400 kilobytes, which is roughly equivalent to 50,000 English words. At a minimum, every item contains a primary key and a corresponding value. Now, when you create an attribute, you must define that data type. And data types fall into the following three categories. We've got scalar, set, and document. We're going to deal with each in turn. So a scalar data type, this can only have, or can have only one value. You can have string, number, binary, boolean, and null. So the string data type, you can store up to 400 kilobytes of Unicode data with UTF-8 encoding. A string must also always be greater than 0. The number data type stores positive or negative numbers up to 38 significant digits. DynamoDB strings trims those leading and trailing zeros. We've got the binary data type. This is also an example of a scalar. It stores binary data in base 64 encoded format. Like the string type, it's limited by that maximum item size of 400 kilobytes. And the fourth example of a scalar is a boolean. This can store a value of either true or false. And number 5, the null data type. This is for representing an attribute with an undefined or unknown value. Oddly, it must contain a value of null. So those are scalar data types. They can only have one value. And then there's the set data type. The set data type holds an unordered list of scalar values. The values must be unique within a set, and a set must contain at least one value. You can create number sets, string sets, and binary sets. So it doesn't really make sense to have a boolean set. It doesn't really make sense to have a null set, but certainly you can have number set, or a string set, or a binary set. Now on to the third category. So we've done scalar, set. We now have document data types. And these are designed to hold different types of data that fall outside the constraints of scalar and set data types. You can nest document types together up to 32 levels deep. So we have a list document type, which can store an ordered collection of values of any type. Notice the contrast with sets. We said that a set was really an unordered set, or an unordered list, whereas here we've now got an ordered list. So we're within the document category. So a list document type can store an ordered collection of values of any type. And then we have an example. Chores, make coffee, groceries, pay bills, bills. Notice that the chores list contains string data, numeric data, and we've also got nested lists there. So that's the list document type. And then we've got the map data type as well. This can also store an unordered an unordered collection of key value pairs in a format similar to JSON or JavaScript object notation. As with a list, there are no restrictions on the type of data you can include. The following is an example of a map that contains a nested list and a nested map. So we said there that at a minimum, every item contains a primary key and a corresponding value. And the point was that when you create an attribute, you must define the data type. You must. And so we were just going into a bit of detail about what the data type might be. When you create an attribute, you must define that data type. Throughput capacity. When creating a table, you have the option of having DynamoDB operate in on-demand mode or provisioned mode. In on-demand mode, DynamoDB automatically scales to accommodate your workload. This is useful if you don't know what your workload demand is going to be, or want to pay only for the capacity you use. In provisioned mode, you specify the number of reads and writes per second your application will require, and this is called provisioned throughput. DynamoDB reserves partitions based on the number of read capacity units and write capacity units that you specify when you created the table. When you read an item from a table, that read may be strongly consistent or eventually consistent. A strongly consistent read always gives you the most up-to-date data, whereas an eventually consistent read may produce stale data that doesn't reflect data from a recent write. Whether you use strongly or eventually consistent reads, that depends on whether your application can tolerate reading stale data. You need to understand whether you need strongly or eventually consistent reads when deciding how much throughput to provision. Note, you can switch between provisioned and on-demand mode, but only once every 24 hours. End of note. For an item of up to 4 kilobytes in size, one read capacity unit buys you one strongly consistent read per second. To read an 8 kilobyte item every second using a strongly consistent read, you would need, in fact, 2 of those read capacity units. Because we're trying to read an item that's twice as big in the same amount of time, so something has to give, so we have to have twice as many read capacity units. We wouldn't need 1, we'd need 2 read capacity units if we were intending to read an 8 kilobyte item. So that was for strong consistency. But if you use an eventually consistent read, one RCU buys you 2 eventually consistent reads per second. So you can get more if all you're after is eventual consistency. To read an 8 kilobyte item every second using an eventually consistent read, you would actually only need 1 read capacity unit. Notice how earlier we said that to read an 8 kilobyte item using a strongly consistent read, you'd need 2 of those capacity units. But if you drop down and just lower and go for eventual consistency, to read that item, you only need 1 RCU. So in a way, for a fixed amount, let's say you've got a fixed number of capacity units, there are either 2 things that can give for you to get more bang for your buck. You can shift from strong consistency to eventual consistency, and that will allow you to achieve more operations, or you can reduce the size of the item you're attempting to read. So that's all about reading data. When it comes to writing data, 1 write capacity unit gives you 1 write per second for an item up to 1 kilobyte in size. This means if you need to write 100 items per second and each item is less than 1 kilobyte, you'll have to provision how many units, how many capacity units? 100. That's very simple. But if you have to write 10 items per second, each item actually being 2 kilobytes, so these are quite hefty items, then you'd need how many capacity units? So you want to do 10 items per second, each is 2 kilobytes. you'd actually need 20 capacity units. You might think that because we're writing 10 items per second, we need 10 capacity units, write capacity units, but the reason we need 20 is that the items are actually quite big. They're 2 kilobytes. And so because we now having to write 2 kilobyte rather than say 1 kilobyte objects, we need twice as many capacity units. So this talk about these capacity units is really about throughput. The throughput capacity you specify is an upper limit of what DynamoDB delivers. If you exceed your capacity, DynamoDB may throttle your request and yield an HTTP 400 or bad request error. AWS SDK's software development kits, they have built-in logic to retry throttled requests. So having a request throttled won't prevent your application from reading or writing data, but it will slow it down. Complete exercise 5.4 to create a table in DynamoDB. Auto-scaling. If you're unsure exactly how much throughput you've got to provision for a table, or if you anticipate that your throughput needs will vary over time, so you don't know how many of these capacity units you need, you can configure auto-scaling to automatically increase your provisioned throughput when it gets close to hitting a defined threshold. Note that this is different from on-demand mode, where you don't have to specify a read capacity unit and a write capacity unit. To configure auto-scaling, you specify a minimum and maximum RCU and WCU, a minimum, maximum write capacity unit, read capacity unit. You also specify a desired utilization percentage. DynamoDB will automatically adjust your RCU and WCU to keep your utilization at this percentage. For example, suppose you set a utilization of 70%, a minimum RCU of 10, and a maximum read capacity unit of 50. So 70%, 10 and 50 in terms of reads at least. If you consume 21 read capacity units, so you've used those up, and you said you want a minimum of 10, maximum 50, auto-scaling will adjust your provisioned capacity to around 30 read capacity units. If your consumption drops to 14, auto-scaling will reduce your provisioned throughput to 20 RCU. So you can see there that it adjusts how much throughput you're provisioned in terms of a number of RCUs. And notice, so we've always got slightly more provisioned capacity than we're consuming. So we consume 21, we get provisioned 30 RCUs. 30 is bigger than 21. If we're consuming 14, how much provision throughput? We get 20 RCUs, so slightly bigger than 14, but we don't go bigger than we need to, but bigger than what we're consuming. Setting the right utilization is a balancing act. The higher you set your utilization, the more likely you are to exceed your provisioned capacity. If that happens, your requests may get throttled. On the other hand, if you set your utilization too low, you will end up paying for capacity you don't need. Reserved capacity. If you need 100 or more WCU or RCU, you can purchase reserved throughput capacity to save money. You must reserve RCU and WCU, so read and write, separately, and you're limited to 100,000 units of each. You have to pay a one-time fee, and you've got to commit to a period of 1 or 3 years. So that's the end of the discussion on throughput. We now finish, well, we've really got 2 things to cover. We're first going to talk about reading data and indexes, and then finally a discussion about global tables, and I suppose you could include backups within that. So reading data. DynamoDB provides 2 different operations to let you read data from a table. A scan and a query. So a scan lists all the items in a table. It's read-intensive operation and can potentially consume all of those capacity units that you've provisioned. A query returns an item based on the value of the partition key. When performing a query, the value of the partition key you search for must exactly match that of an item. If your table contains a sort key, we said that a composite key consists of a partition key and a sort key. If your table does contain a sort key, you may optionally query by the sort key as well. For the sort key, you've got more flexibility. You can search by exact value, a value greater than or less than the key, a range of values, or the beginning of the value. Okay. So that was about a scan and a query. Do we get all the items or just one item returned? Secondary indexes. Secondary indexes solve two issues with querying data from DynamoDB. When you query for a particular item, you must specify that partition key exactly. For example, the author table you created earlier has last name as the partition key and first name as the sort key. Well, secondary indexes let you look up data by an attribute other than the table's primary key. Think of a secondary index as a copy of some of the attributes in a table. The table that the index gets its data from is called the base table. When you create a secondary index, you can choose which attributes get copied from that base table into the index, and these are called projected attributes. A secondary index always includes the partition and sort key attributes from the base table. The question is just which other attributes does it contain? Which projected attributes should it contain? You can choose to copy just the partition and sort keys and their values, the keys plus other attributes, or everything. This lets you extract only the data you need. There are two types of secondary indexes: global secondary indexes and local secondary indexes, and we're going to see that there's a few constraints on local secondary indexes. They're a bit more demanding. For example, you can create a global secondary index anytime after creating a table. In a global secondary index, the partition and hash keys, we said earlier that hash key was another word for partition key, but the point is, in a global secondary index, the partition keys can be different than the base table. The same rules for choosing a primary key still apply. You want the primary key of your index to be as unique as possible. If you use a composite primary key, items having partition keys with the same value will be stored on the same partition. When reading from a global secondary index, reads are always eventually consistent. So we can't get that strong consistency with a global index. If you add an item to a table, it may not immediately get copied to the secondary index. Now on to local secondary indexes. If you want one of these, they must be created at the same time as the base table. You also cannot delete a local secondary index after you've created it. The partition key must always be the same as the base table, but the sort key can be different. So that is a major difference. Okay, earlier when we looked at the global secondary index, the partition keys can be different than the base table, but here the partition key must be the same with a local secondary index. But the sort key can be different. For example, if the base table has last name as the partition key and first name as the sort key, you can create a local secondary index with a partition key of last name and a sort key of birth year. So we've changed the sort key. It used to be the first name, now it's the birth year. Reads from a local secondary index can be strongly or eventually consistent. So they can be strongly consistent here depending on what you specify at read time. So as a quick summary, there were a number of properties that differentiated global and local secondary indexes. First, creation time. Global secondary indexes are relaxed. You can create them anytime after creating a table. Not the case with local. The second property by which they differ relates to the partition key. With global secondary indexes, the partition keys can be different, again, more relaxed with global, but with local secondary indexes, the partition key must be the same as that base table. So that's the second point of difference. The third point of difference relates to whether strongly consistent reads are permitted. They're not with global secondary indexes, so in this respect, global secondary indexes turn out to be a little bit strict, in fact, for this third property, because it's with local secondary indexes you can have that strongly consistent read. Property number 4 relates to the deletion. Well, we're told that local secondary indexes cannot be deleted after you've created them. Presumably you can delete global secondary indexes, but they never explicitly state that. It would be nice if the discussion was a little bit more systematic, but I've got 4 points of difference there. Okay, and now the final discussion we're going to have about DynamoDB relates to a feature called global tables. Global tables. To improve availability, you can use global tables to replicate a table across multiple regions. To use global tables, your table must be configured in on-demand mode or provisioned mode with autoscaling enabled. A global table is a collection of replica tables, and a global table can only have one replica table per region. Whenever you write an item to a replica table, it's replicated to replica tables in other regions. Global tables don't support strongly consistent read across regions. So presumably you've got strong consistency within a region? Yes, no, we don't know. Notice that this is somewhat similar to the multi-AZ feature that we saw with RDS, in that this pertains to availability. It's to do with failover. Presumably though, this does also improve the performance of your table. So it's this hybrid solution. It's helping with performance because presumably if you have something based in the UK, an instance in the UK, and you've got customers in Australia, they will get better performance if you've got global tables compared to if you don't have global tables enabled with your DynamoDB table. But it's also dealing with this aim that we have to make things tolerant of faults, things failing. So that's all we say about global tables. Backups, you can back up a table at any time without consuming any read capacity units, those things we measure throughput in, or without impacting the performance of DynamoDB. And you can take an unlimited number of backups. And now let's talk about restoring the backups. You can restore a backup to the same region or a different region to the table the backup was taken from. When you restore a table, you can specify the destination table should operate in on-demand or provisioned mode, and you can specify the options for indexes and encryption. The point being made there, I think, is just that there's some flexibility in backing up. The backup, when you restore from a backup, it doesn't have to completely exactly copy the thing you had before. You can change things slightly. And that's the end of our discussion of Database Services Chapter 5. And just one final note that I'm making, multi-AZ was at the availability zone level, this feature of RDS. This thing that we get with DynamoDB, the non-relational service, which is called global tables, this is at the regional level. And as I said, it appears to help us with our aim of both performance and fault tolerance.